Good morning, class, and welcome to this lesson on Fluids 1, Density and Pressure. Today we are just going to define density and pressure and be able to explain the major characteristics of each one of those. So, first off, before we even talk about density and pressure, let's talk about what a fluid is, because this actually could be confusing in some situations. A fluid is any substance that flows. Any substance that flows. So really, in general, a fluid is both gas and liquid, or liquids. We tend to associate fluids with liquids because generally when we're talking about fluids, we're talking about water or sweat or blood or stuff that has to do with our bodies. But reality is fluids really are gases and liquids because gases flow as well. Air flows. And since we're going to be talking about density and pressure, air exerts a pressure. Air has a density. And so really we need to be able to discuss density and pressure in general terms of all fluids, and that's both gases and liquids. And so this is a very important point to make because some of our problems are going to involve both pressure from a liquid like water and then pressure from a gas as well at the same time. And so we need to be able to calculate both those things based on that. So fluids are any substance that flows. So let's move on. Let's talk about density. Density. Sometimes this is also referred to as mass density. And so I don't want you to get confused if you hear this term and be like, oh, we never learned about that. Mass density is density. Now, density is commonly known as, the symbol for density is the Greek letter rho. This is rho. Okay, it's kind of like a P, but it has a curve in it, and it comes down here like that. So rho equals m over v, mass over volume, mass over volume. And with this, I'm going to give you a little thing I've learned from one of my teachers back in high school. If you ever forget the formula for density, just remember that love is dense. Love is dense. And because love is dense, we will draw a heart because of love. And we draw a line through it. And if you notice from this line, we have like an M on top and a V on bottom, M over V. Love is dense. So that's just a little kind of a fun way to remember what density is. So density is mass over volume. Okay? And now density is really hard for people to, it's very easy to confuse with other things. It is easy to confuse density with mass. Okay, density with mass. And this is where we get the very common question of let's go to the next page, of what's heavier? What's heavier? Well, 1 kilogram of feathers. Notice I put kilogram instead of pound because I'm in a physics class. 1 kilogram or 1 kilogram of lead. Okay? So we have a big old bag here of a bunch of feathers. Okay? It's more like a leaf. Okay? A big old bag here of a bunch of feathers. Okay, I'm not going to draw all of them. Okay? And then we have a very small thing of lead. 1 kilogram, 1 kilogram. This is lead. Okay? So what's heavier? Kilogram of feathers or a kilogram of lead? And so really what we're saying is what has the greater mass? What has the greater mass? And the reality here is neither of them do. They have the same mass. 1 kilogram equals 1 kilogram. They have the same exact mass. And where we get confused is density. Density. Which one is more dense? Which one is more dense? Well, you can imagine that a kilogram of feathers is going to take up a very, very big space, and a kilogram of lead is going to take up a very, very small space. And so really, a kilogram of lead is more dense, meaning the atoms or molecules that make up lead are going to be closely packed together. If we were able to zoom in on this, if we were able to zoom in on a piece of lead right here, and we blew it up, and we're looking at the molecule, the molecular level, these little molecules of lead that are all connected together are very, very, very close together. These are all lead molecules. So if we did the same thing over here, and we zoomed in on these feather molecules, we would notice these are very, very spread apart. Okay? Very, very spread apart. Notice how close these are together versus how close these are together. Okay? So density really means how much mass does one space take up. So if I did the equation for both of these, if I did the density of feathers is 1 kilogram over, we'll say, I don't know, 5 meters cubed, okay, volume. And the density of lead is 1 kilogram over 1 meter cubed. These numbers are not accurate, by the way. The density of feathers would be, 1/5 kilogram per meter cubed, and this would be 1 kilogram per meter cubed. So you can see from the math right here that lead is more dense than feathers, even though those are just numbers I made up right now. So that's what density is. How much space does something take up? Metals tend to be dense. Metals tend to be dense. Okay? Liquids tend to be dense. Okay? Pretty much every situation I can think of, gases are always going to be less dense than both solids and liquids. Okay? These might depend, these might go back and forth on which one's more dense or whatnot. Solids tend to be more dense than liquids. They tend to be, but that's not always the case because some things do float, like on water. So, but gases are always less dense than solids and liquids. Gases are very, very spread apart, and that's what actually makes them a gas, one of their characteristics. So, this is density. How much space does something take up? Kilograms per meters cubed. So let's move on now and talk about pressure. Let's talk about pressure. So pressure, the formula for pressure is force over area. And I'm going to write this in here, the magnitude. The magnitude of the force, meaning force in this sense is not a vector. Is not a vector. Okay? So pressure equals force over area. That means pressure is not a vector because we're not looking at the directional component of force. We're only looking at the magnitude, the number. So pressure is equal to force over area. Pressure is very simple. If you divide over a smaller area, you get a greater pressure. If you divide over a larger area, you get less of a pressure. So for example, let's just, let's take a hammer or a nail and a hammer. Okay? When we apply a force to a nail, we apply a force, and we really are applying a force over a very, very small area. Small area. Lots of pressure. This is lots of pressure. And what that's really telling us is that, these nails do damage because they apply so much pressure. Because that's the point. Do you get it? The point is that if we go over a very small pressure, it will pierce into the material like wood and cut right between it. Okay, it'll just go right through it because it's applying so much pressure. And so, for example, let's go on the flip side. Let's do another example of like snowshoes. Examples like snowshoes. What are snowshoes? Snowshoes, if we have our foot right here, snowshoes are really just like pretty much like big tennis rackets. Okay, and so you're sitting on this snowshoe. There's like some sort of netting on it. And so what is a snowshoe doing? This snowshoe is taking your weight or force and dividing it over a larger area. So if we get force over a larger area, so if we have a larger area, we have less pressure, and so therefore you won't fall into the snow every single time. You'll stay on the snow, on the top of the snow, because it has a smaller pressure. So pressure is equal to force over area. Okay? Pressure is not a vector, and pressure is perpendicular to all surfaces. I'm writing on the board right now, so I'm gonna draw a board up here. There's air pressure pushing up against this board right here, and this same pressure, there's tables in the room right now, this pressure is pushing down on the table, and the same pressure is pushing up on the table. Okay? And my computer monitor is slanted at an angle right now, my computer monitor, and the pressure is there's pressure applied perpendicular to all surfaces. So pressure is perpendicular to all surfaces. Doesn't matter if they're sideways, down, up, angled, left, right, doesn't matter. Pressure is perpendicular to all surfaces, and that's the direction it applies. If you think about pressure in a tire, okay, there's air pressure on the inside of the tire pushing out, and it's pushing out perpendicular to each surface in all directions, okay? Perpendicular to each surface in all directions. So pressure is always perpendicular to a surface, and that is an important point to know when we start getting into more in-depth equations. And so I just wanted to wrap this up with some units. Pressure is known as force over area. So Newton over meters squared. Force is newtons. This is the units. And this Newton over meter squared is known as the Pascal. Okay? This is known as pascals. Okay? Newtons over meters squared. And this is going to be our most common unit in physics. Okay? There is also units of atmospheres, ATM. Some people use this. There's unit of millimeters of mercury. Some people use that. There's also units of bar. And there's also PSI. Okay? So at sea level, this is an important thing to know. It'll always be given to you on a test. That at sea level, 1.013 times 10 to the fifth pascals is the same as 760 millimeters of mercury, which is the same as 1 atmosphere, which is the same as 1 bar, and I don't remember how that relates to PSI right now. I will add that later. So these are all related to each other. And so if we ever have a question in atmospheres, we probably want to convert to pascals first. Or if we have it in millimeters of mercury, we want to convert over. So these are all of our conversion units right here. Okay? By the way, and in America, many of you know this, PSI stands for pounds per square inch. Okay, so PSI is pounds, or force, over inches squared, which is area, F over A. So that's the most common unit in America, and it's one we always use. For this class, we will be using a lot of pascals, but we will be converting from these as well. If you ever forget these, or you don't have your notebook with you, you can always look these conversions up in the front of your textbook. Pretty much every single physics textbook has all of these in the very front for conversion tables.